This is a video about bingo, so it feels appropriate that there's a bingo card so you can play bingo while learning about bingo. These are things you may or may not spot in the video. We asked the Stand Up Maths Patreon supporters to suggest what they would put in a bingo card. But don't use this one, because if everyone's using the same one, you're all going to win at exactly the same time. So in the description of this video, I will link to a Dropbox folder with 10,000 randomly generated versions of this. And they will have different things in them. We've got a set of 75 possible things you're looking for, and you will have 24 assigned to your bingo card. So in theory, you will win at probably a unique moment. Comment below if you think you've had the earliest point in the video where you've won. But I can guarantee one thing. It's for everyone watching this video. Let's say there are thousands of people playing bingo simultaneously, and these have been assigned randomly. Your card is different. I guarantee it is 3 times more likely that the person who wins matches a horizontal line compared to a vertical line. And it's true. That's a mathematical fact. And you might think that's ridiculous because this is just a standard number bingo sheet. You might think, well, hang on, what about proof by just turning it over? Like, how, if they're random, how on earth can horizontal be 3 times more likely than vertical on the winning bingo card when you could do this? But it turns out there are some subtleties in the game of bingo. By the way, my book, Love Triangle, which is out now, I know I mention it a lot, it's probably on the bingo card, but it was a #1 bestseller. Isn't that incredible? If you had got the Sunday Times a couple of weeks ago, which I did, you flick through to the culture section, and there it is, Sunday Times bestsellers. Hardback, general, that's me, Love Triangle, #1. We beat House of Beckham, which was meant to be #1 into position #2. Hilarious. So thank you so much to everyone who bought the book. It's been so busy and frantic since it came out, I haven't really stopped to celebrate. So this video, in theory, is to celebrate #1 bestseller. These are still available on Massgear, by the way, and people keep asking, so I say if you do buy this off Massgear at the moment, we are still doing the limited edition triangle covers. So if you buy it on Massgear, not only will it be signed by me, but on the back, oh, this is number 76. On the back, I've individually numbered all of them and initialed them and signed them. You get both covers, Massgear. I'll link to it below. Thank you so much to everyone who's buying them. Please keep buying it. I still have a lot of these left. I'd really like to sell them. I committed to a lot of first editions for you. Don't let me down. And if you did want one, but you're in North America and the postage from the UK was so expensive, I appreciate that. The US edition is out today. Yes, you can buy Love Triangle in your own country. You'll get free shipping. You can probably get it at a discount on Amazon. I'll put my affiliate link below. But if you do want to get a copy of Love Triangle, please do buy it from anywhere this week, because then there's a chance we will get into the New York Times bestseller list. Wouldn't that be amazing? Come on, buy it this week. I feel like that's the right amount of parasocial guilt. And now, on to bingo. Oh, so the first number out was 28. I'm just quickly checking. I generated 3 bingo cards a second ago. No 28s, so nothing to mark off. We will then spin this. This cost £6, by the way. Cheapest bingo set we could find, because we take good use of Patreon's funding seriously here. Oh, okay, next number. What do we got there? It's not 7, number 11. I think I've got the idea down for being a bingo caller. So now I'd look through 4 and 11, no 11, no 11. Oh, and 11, there's an 11 there. Right, I gotta mark that off. And there it is, 11. We are off and racing. Now, some of you will have noticed something odd about this bingo card. It seems that there are small numbers on one side and then they get gradually bigger as you go across the columns. And while they are random, it's this kind of, not an ordering, but they're subsets of numbers. That's what means that rotating it this way is different. Like that is a fundamentally different bingo card. Now I've rotated it, which is why this way up. Horizontal matches are way more likely to be on the winning card. than vertical ones. And we can have a look at the exact details of what's going on there on this whiteboard. I just realized I've drawn that grid, so from my perspective it looks like a proper grid, but straight on it looks a bit skewed. Sorry about that. There you are. So we've got 5 columns and 5 rows. The middle one is like a free space, so you get that no matter what, and then we're actually going to ignore the probability of getting diagonals. They do change the math slightly, but not enough to worry about for now. We'll deal with that later on. So we're just going to look at your probability of winning on a row or on a column. Now, this has a subset. It has 24 of the numbers from 1 to 75 filled in there. However, they're not equally likely to go anywhere. This first column here, which is often labeled as the B column, that B column has 5 numbers selected from the numbers 1 to 15. So this column here is everything from 1 to 15. The I column is then everything from 16 to 30. The N column, 31 to 45. G is 46 to 60. O is 61 to 75. So in one sense, the numbers from 1 to 75 are equally likely to appear in the grid, with a mild impact that the numbers from 31 to 45 are slightly less likely. That actually doesn't make a difference to what we're doing here. So you can still look at it and go, well, it's random, but somehow by putting them in these categories and then putting them in, it's changing the probability. It's changing the odds of what the winning line will be. And it was my friend Art Benjamin who originally showed me the bingo paradox. They wrote a paper in 2017 with Joseph Kissenweather and Ben Weiss, and it goes through the mathematics behind why these categories change the probability so much. Just to clarify our terms here, we are talking about a lot of people playing bingo at once. So there's a single string of numbers coming out of the bingo spinner, and then eventually one person wins, and whoever that person is, it's 3 times more likely they had a horizontal row than a vertical row. And Art and their collaborators did simulate that in software. That's what I would have done. They probably used something better than my terrible Python code. But they generated 1,000 random bingo cards, and then they simulated 100,000 games where those same 1,000 people are playing bingo at once. And in that situation, they had a result that it was twice as likely to get horizontal winners as vertical winners. While simulations are helpful, we are of course going to go through the proof in general that they do in the paper, and it's very nice. But the thing I want to pull out from that example is that we're imagining a big room of people all playing at once, and that's going to give us our first assumption to make the maths a little bit easier, and that is if a series of balls come out which hypothetically could win a game of bingo, we're going to assume so many people are playing at once that someone will have a card where that has won. Now, to do the working out, we're going to use the other side of the whiteboard. Spent a lot more Patreon money on this than we did on the bingo spinner. The first number that comes out, we don't know what it is. We're just going to call it X. In our case, it was 28. That's the first one. Actually, we're going to call it X1 because it's the first number that comes out. The second number, which in our case was 11, we're going to call X2. And then we'll get a third number. Let's just get one of those. Here it is. Our third number is, we got that one for free, number 3. So there we go. Now, no one can win yet because we haven't got enough numbers. So in theory, you would need at least 4 for these ones to be able to win, because you could use the null in the middle. So we could argue that once we get to X4, that's it. It's a possible winner. Like I said, that complicates the maths. So for now, we're going to ignore the center one. We're going to assume you need to have 5. So X5 is the first opportunity for someone to have 1. And a quick clarification here on both words and numbers. We have something that we call the bingo sequence. That's the order in which these 75 balls come out of the bingo machine. And that's 75 factorial. There are so many possible bingo sequences, it's ridiculous. That's 2 times 10 to the 109, more than the number of atoms in the universe. You know how this works. Big number, ridiculous number, and we will actually have to use that at some point in our calculations, but in practice, you're never going to need that many balls. You're going to have a game where someone's won way before that. But hypothetically, that's the space of possible bingo games coming out of the bingo spinner thing here. We also have, as opposed to the bingo sequence, bingo cards. Now there are far fewer of these because, once again, actually we factor in the null again. There's one column where you're picking 4 from 15, so it's 15 choose 4, and then 4 columns where it's 15 choose 5. And so that's 15 choose 5 to the power of 4. Multiply them together. If you factor in the null, that's 111 quadrillion possible bingo cards. Actually, here's the full number. Of course, we worked it out. It's maths. You can do it precisely, or rather Wolfram Alpha count. And if you're playing along with the Stand Up Maths bingo card, of those possible 111 quadrillion cards, I generated 10,000 of them at random and put them in the Dropbox folder. Dropbox do say they can have up to 300,000 files in a folder. I didn't want to push my luck. 10,000 is plenty. So assuming the moment the 5th number comes out of our bingo sequence, there is a possible winning play, and there's so many people playing that someone will have it, we can now calculate what's the probability that these are such that it could be a horizontal match, and what's the probability it could be a vertical match. We will do horizontal first. So when the first number comes out of our bingo sequence, doesn't matter what it is. 100% of those, 1 from 1, mean that we're in the running to have a horizontal win. The second one, however, has to be from a different column. So whatever column this one's in, those 15 numbers, we don't want to see them again because we need to get 1 from every single column from the first 5 to plausibly have a horizontal win. So the other 4 columns, where there are 60 numbers in the other 4 columns that the second one could be from, and because we've already removed 1 ball, there are 74 balls remaining in the bingo spinner. We've now got 2 columns. If we want to get the third column, well, that's any of the remaining 45 from the other 3 columns, and there's now 73 left. Then we're down to 30 out of 72. And finally, any of the 15 in the remaining column we don't have yet, out of the 71 that are still on the spinner. You multiply all those together, the probability that someone who wins after 5 balls is 0.04400. Not bad. So there's a 4% chance of a horizontal win after 5. What's our probability for a vertical one? Well, we can do pretty much the same logic. The first ball that comes out, doesn't matter what it is. It's in one of the columns somewhere, that's good enough, 1 out of 1. We now need the next 4, if we're going to have a vertical win, to all be in the same column. So they're all coming out of that same pool of 15 possible numbers, of which we've already had 1. So the second one has to be one of the remaining 14 numbers out of the 74 left to draw from. This one then has to be the third number in the same column. So that's any of the remaining 13 we haven't used out of 73, the remaining 12 out of 72, and finally the last 11 out of 71. And you can already see that vertical is way less likely than horizontal because these at the bottom here, the denominators are all the same, but the numerators are way smaller. In fact, if you multiply all these together, it equals 0.00087. So less than 0.1% chance that the 5th ball gives you a vertical win. And look, that is way, way less likely than this. As they note in the paper, so a horizontal sequence is about 50 times more likely than a vertical sequence on the 5th draw. 50 times! Obviously, it doesn't always stay that bad, and as you have more and more numbers coming out, for each one we could work out the probability for horizontal and the probability for vertical. For example's sake, I'm going to do what they did in the paper here, and we're going to try and calculate it for the 10th number coming out in the sequence, which is a lot more complicated, but I think it's going to be worth it. Future Matt here. I just wanted to clarify if you're thinking, but the video's done. All the maths is complete. It's because we've only done it for if someone wins on the 5th ball out. And it feels very conclusive because past Matt wasn't particularly clear, but we also have to do the maths for if it was on the 6th ball, the 7th ball, all the way through. So that's why past Matt's going to do the example for if someone happens to win on the 10th ball, which isn't special. It's just one that we're going to do as an example. And at the end of the video, we will show the complete combined result for all the different places a bingo sequence could terminate. If you want the answer, you can skip ahead now. If you want to see the working out, I'm going to go make some coffee. And then, this is not coffee, this is water. If you ticked off coffee on the bingo spreadsheet, you are wrong. Drinking water from the mug. In a second, it'll be coffee. Now it's coffee. Or is it? Mark it down at your own risk. So this is the case where n equals 5. So someone won on the number 5 ball out of here. And this is the case for n equals 10. Without any loss of generality, we're going to assume that the very 10th one that comes out, so this is the one where someone wins, and we're going to do the calculation for a horizontal win. We're going to say that's ball number 75, which means it comes out of the collection of O. So I'm actually going to now refer to these different sets as just set B, that's 1 to 15, set I is 16 to 30, and so on. So the very first one's from set O, somewhere in 61 to 75. Specifically, we're going to say number 75. It could be any ball from any set. But what that means is these other 9 here, well, we can deduce a few things about them straight away. First of all, none of them can be O, because we know when this one comes out and it's O, that's the winning move. And so that has to be the first O that appears because it's completing that row. And it means the rest here have to be from B, I, N, and G. And we need to have at least one of each so that our O at the end here can complete a total horizontal match. So we now just calculate that probability for this case, for this ball, multiply it by 75, and we have the probability it happens at all. So what could these look like? Well, we could have one of them could be a B. In fact, we could have B, 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 up to 4 Bs. We can't have a 5th one because then that could possibly be a matching vertical one. So that's the most we can have of Bs. We could then have, I don't know, let's do 3 Is, 1 N, and 1 G. That's 9 in total. There's no 5 of any one of them, and there's at least 1 of each. And we could summarize that as being 4, 3, 1, 1. Now, there are other 4, 3, 1, 1s. That could also be B, I, N, G, G, G. That's also a 4, 3, 1, 1. We're just saying there's 4 of one of them, 3 of another one, and then 1 each of the remaining ones. And we can fill in every possible variation on that afterwards, but it kind of makes life a bit easier to clump them into families. So we got one family which has, as I said in the paper, the shape of 4, 3, 1, 1. There's another family which is 4, 2, 2, 1. There's 4, 3, 3, 2, 1. Finally, 3, 2, 2, 2. So these are the 4 possible families of shapes of results we could get for those 9. As I said, there's multiple ways you can get 4, 3, 1, 1. In fact, there are 12 different ways you can do it, and you can follow through that if you want. There's 12 different ways you can get this one. There's 12 you can get that one. And this one, because there's 3 2s, actually reduces it. There's only 4 ways that you can have a unique way of assigning BING to that shape. Now, we're just going to focus on this first one here, but again, what we do for this one, we can apply to the other ones in a moment. So now taking this one here as our starting example, and we've got to actually assign numbers to this now. So what could these B's be? Well, there are 15 possible values in the set of B, of which we need to choose 4, so that's 15, choose 4. We then multiply that by, well, there's 15, choose 3 for the I's, and then there's 15 choose 1 and 15 choose 1. So that's all pretty straightforward. And you can see already, given this is just 4, 3, 1, 1 at the bottom, how we could fit these other ones in for their cases. And now we need to expand it out to include everything else. So how many possible sequences match this? Well, first of all, there's every conceivable way you could have arranged these within here, because they don't have to be BBB in that order as they come out. So we need to multiply this by 9 factorial to take that into account. Technically, in a moment, we want to divide this to get a probability out of all 75 factorial possible bingo sequences, which, as we established, is a lot, which means we need to think about all the ones after the 10th one. I mean, there's another 65 of them to come, and they could be in all sorts of orders. So we're going to chuck in a 65 factorial here, and I find it fascinating that there's, like, this number's practically incomputable. I mean, you can compute it, but it's got over 100 digits. It's such an unimaginably large number, as is 65 factorial. But we're using them because they're going to kind of cancel each other out, and we'll still get like a nice, neat answer at the end. I find it hilarious that technically in isolation, parts of this hit such huge extremes, but yet we get a nice, simple result out the other side. Anyway, we now need to factor in our other steps here. So we're all the way down to here. We need to multiply by that 12. We need to multiply by that 75. Future Mac clarification, we're not multiplying by 75 because that's the number of the last ball. We picked that one arbitrarily. It's 75 because there are 75 possible balls, which could be last. We've only done one, so we've got to multiply it up. 9 factorial times 65 factorial times 12 times 75. So the probability of someone winning with a horizontal match on the 10th number out for this shape specifically, but every combination within it, equals 0.01517. We now just need to do the equivalent thing for the 3 other shapes. We add them all up and we get the grand total probability of the match being horizontal, which I'm just going to read off the paper here. It equals 0.09415. 0.09415. There you go. And that's what Art and their collaborators did. They calculated, first of all, this for every single shape for the case of n equals 10. And then they repeated the whole process for a vertical match. And then they did that for every possible n value. In this table here, there's their final results. You might be wondering, though, why it stops at n equals 17. And that's because that's the last possible moment when it either goes horizontal or vertical. And there's 2 reasons why assuming if someone can win, they do simplifies the maths. One is this one, because up to 16, then you've had like 4 of each of the other columns. And the next one, the 17th one, either has to make 5 all in the same column, or it makes a complete set of 1 from each of the columns. And because we're assuming someone will win as soon as they can, it means we can stop the count there. It also means that you cannot have someone winning horizontal and vertical at the same time, which would again confuse the mathematics. But to win horizontal, you need to be the first time you're getting 1 in the winning final column, and to win vertically, it needs to be the 5th time you're in that column. And a ball coming out cannot both simultaneously be the first one from that set and the 5th one from that set. So the assumption of someone definitely wins as soon as they can, again, simplifies the math there nicely. We add up all the probabilities of a horizontal on n, ph subscript n, and the probabilities of vertical, and we get a 75.2% chance that the winning move was horizontal and 24.8% is vertical. So basically 3/4 of the time horizontal, 1/4 of the time vertical, and that is our ratio of 3:1. We can also finally deal with the middle blank space because Joe Kissenweather and Dick Hess did run the calculations for what happens once you've got that free space in the middle, and it does change the probability slightly. It now means a horizontal win is 73.73% likely, and the vertical win is therefore 26.27% likely. So there's our final ratio. If you're playing stand-up mass bingo at home, or any bingo where you've got a free space in the middle and you're pulling 5 from sets of 15 for a total of 75 options, it is a 2.8 to 1 ratio of someone winning on a horizontal versus someone winning on a vertical. The bingo paradox is true, and we have now put some numbers on it. Much like the game of bingo. It's got numbers on it. And in conclusion, I would like to tie this back to my book, Love Triangle, now the Sunday Times #1 bestseller, and soon to be New York Times bestseller. Come on, you're gonna buy it, do it. And I can do that slightly clunkily because as well as 2 people, Tom and Mike, sending me in crosswords that they made based on my book, I'll link to those below, my friend Eliane McDonald has made a bingo sheet for the book. So I'll link to that below. You can follow along with the bingo sheet while you're reading the book. And as I mentioned earlier in the video, you can still get the Triangle edition based on the blueprint by Paul Catherall if you buy it on Massgear. Sadly, the other 2 ones are sold out. Well, I say sold out. I have got 2 here. So this is a very, very rare simplex one. There's only 1001 of these, of which this is one of them. Number 653, and I've got a still quite rare but not as rare tetrahedron one. There are only 2024 of these, so you can go and buy any copy of Love Triangle on Massgear and you'll definitely get one of these, but all 3 of them, and give me a second. I now have 3 of these, 1 of each cover, and when it dawned on me, because this is the most limited one, there's only 1001 of them, and there are only 168 prime numbers below 1001, of which this is 1, then it's plausible that I could make 168 box sets which have all 3 of the covers based on Paul Catherall's excellent prints in a cuboid. And what I find particularly pleasing is that the covers are based on Sidler's shape. Oh, actually, I'll grab them. They're right over here. The covers are based on Sidler's shape, which is the complicated one from the 1960s. And because I was then doing a box set of matching prime numbers together in a cuboid, I thought I could make the design of the box is based on the cuboid-based version of the same type of shape discovered by my friend Robin Houston 2 years ago. And so there, look at that. What an object. Now, these are too expensive. You should not buy these. We're selling them for £168 a box set, which is too much for buying the same book 3 times. But if you want to support the channel, I'm going to use the money from the box sets to do a video in the future, and I will name you in the credits of that video to say thank you for buying the box set and funding the channel. And if you really, really want the other ones, it is the only way to get the simplex and the tetrahedron versions of the cover. And while we're selling stuff, Paul Catherall has actually made a run of prints based on these designs. You can buy them from his shop if you want some original artwork. They're very cool. Link below. And all 3 of them will match. Oh, it's so nice. I cannot guarantee you'll get this one. You know what? I'm going to write, I'm not signing the boxes because frankly, this comes with 3 numbers, 3 initials, and 3 signatures already on the inside books. But given this is prime number, was it 653? 653. I'm going to sign exactly 1 cuboid set. So on the back here, I'm going to write on screen, number 0653, and then 1 more signature. I've signed so many things. So I will give this randomly to 1 person who orders the box set on the day this video went out. So if you order it today, there's a 1 in N, where N is smaller than 168 chance that you will get this one, but you'll definitely get 1 of them. And the standard one with the, I still think, absolutely incredible triangle cover. You get that and the original cover if you order on MassKit. That's enough of me talking about my book. I put so much work into this and I've signed so many and I didn't have to do any of this ridiculous extra stuff, but I wanted to do it and I hugely appreciate if you can order it. It will be cheaper when it comes out in paperback next year.
This has been a Stand Up Maths production for the Stand Up Maths Network. Filmed and edited by Alex Ganbash, produced by Nicole Jacobus, written and performed by Matt Parker, and while I'm here, you should definitely listen to the podcast A Problem Squared.